of the characteristic of singularity theory. You go from the maps to vector fields, okay? In order to find your infinitesimal objects. So, and this infinitesimal object is given by the tangent space to G orbit of F. And as the group was the semi-direct product, the tangent space is just the sum of the two tangent space of R and H. So this is the tangent space of the tangent space, and this is the extended tangent space. So this first part here corresponds to the tangent space and the extended tangent space to the group R. And this model generated by df dxi is exactly the Jacobian model of F. And this part here that corresponds to the tangent space of the group H is ON model generated by matrices Cij and RLK, which are the following. So what's Cij? Cij is a matrix that has in its ith column the jth column of the matrix M, and the rest is 0. The other entry is 0. So you put the jth column in the ith column, and the rest is 0. And the same with rows. You put the case row in the else row, and 0 in the rest. I give you one exercise here. Try to show that these vector fields, all vector fields in this model, are tangent to the variety of the maximal minors, right? In other words, this model is contained in the der log of the variety as defined by Juanjo in his lecture. Okay? It's not too difficult to verify that these matrices are tangent to the strata of the variety. Okay. This group, as well as the other group I mentioned, they are geometric subgroups in the sense defined by Jean Damon. And so it follows from this that all the machinery of singularity theory holds, right? So, and I just recall quickly what are the main notions. So for instance, we say that G is stable. It's the extended tangent space is the whole space of deformations. I can give you another exercise that you may try to prove. Can you prove that any generic determinantal variety is defined by stable matrices? So let's do one example. And I take this opportunity to show you the determinantal singularity, which is has isolated singularity and is rigid, right? So let's look at F from C6 to the space of 2 by 3 matrix, right? And let's look at the variety, which in fact I can think of even as the identity, right? So here we have what we denoted by M232. That's a variety of matrices of rank less than 2, which is generated by the 2 by 2 minors of the matrix. So I take here generic matrix in 6 variable. And then if I look at the Jacobian model generated by this matrix, I have here a model which is generated by the canonical vectors in each position, right? So derivative with respect and so on, in such a way that this map here is surjective, right? So in other words, just the Jacobian model generates the whole space. Okay, so the model generated by this is the whole space. That's the point, because it's a space of dimension 6, and I have here a basis for the space. Okay? So this is the idea that you can use to prove that the generic determinant of varieties are indeed stable.
Excuse me.
Sure.
For the students, could you explain the meaning of rigid object?
Sorry, meaning?
The meaning of rigid object.
Yes. Stable. What is the meaning of stable? Stable is something that remains with the same qualitative type by small perturbations, right? Some people or some other areas use the term rigid for one singularity that remains invariant by perturbations, okay? As we explained in the previous lecture, our model objects, which are the generic determinant of varieties, they are then universal and rigid in this sense. Right? Another important concept is the finite determinacy. So given two maps, F and G, we say that given a map, F, we say that it's G finitely determinate if there exists K, such that for all other G, such that the K jets of the entries coincide for some K, then they are G equivalent. If we can say in this case, given such a K, we say that F is K, G finitely determinate. And finally, as in the previous course, we can define a G equal dimension of F as the dimension of this quotient as vector space. And then you can see here that the germ F is stable if and only if the codimension is 0. Okay? So from, we can define this codimension here. We can call this codimension determinant Turina number. And when we are considering the class of Cohen-Macaulay codimension two singularities, it happens that the determinant Turina number and the Turina number coincide. Okay, where the Turina number is the dimension of the space T1 of the singularity, which is the space of all first-order deformations, right? Then in this case, the two invariants coincide, but in general, no. Okay. So this theorem from median thesis is a natural consequence of the fact that the group G is a geometric subgroup of the contact group. So we have the following equivalence. The determinant Turina number is finite if and only if F is G finitely determinate, if and only if F has a versal unfolding with this number of parameters. Right? So we saw in the course of ISIS that versal unfolding, to have a versal unfolding is equivalent to have a transversal unfold. In other words, that the family, the unfolding, being a family transversal to the orbit, is equivalent to the fact that this unfolding contains information of all other singularities that you obtain when you perturb your singularity. And from the fact that the codimension is finite, right, we can compute a basis for the normal space, and we can, in a simple way, write a family which is a stable unfolding, as we did in the previous course, as we did in the previous part of the course. Maybe there's one thing, interesting thing that we can say here, which is the following. So you have F defined in some neighborhood here, and here is the space of matrices. Suppose that this is a representative in some neighborhood here. And we look at this quotient. So we look at this quotient at the origin to define the codimension. But I can define a sheaf of modules in such a way that I compute in each point in the neighborhood of the origin here, this quotient at the point, right? So to say that this dimension is finite is the same thing as saying that this sheaf is supported at the origin, right? Because it represents something of a dimension 0. And if it's supported at the origin, it means that at all points in a neighborhood of the origin, the stalk has dimension 0, or in other words, the map F is stable outside the origin. And then only at the origin, it perhaps is not stable. So this is the justification for the geometric criterion of G determinacy, right? Because if the sheaf is supported at the origin, right, of course, the germ is finitely determinate, right? And in the other direction, if it's supported at the origin, it says that F is transverse away from the origin, right? And being transverse away from the origin, it means that the variety defined by F is an EIDS. Okay? Yes?
I think the last line, there must be a mistake that this is an EIDS for all t smaller, less or equal than n. Because if you put t, the minimal one, so that you have 1 by 1 minors, then usually this variety does not even have expected dimension. So
oh, yeah. No,
I'm afraid
right. Sorry. Yeah,
that
sure.
I think it has to hold for the maximal minors.
Sure,
So
sure. In
T
fact,
equal
as I
N.
said, in fact, the group G acts at the whole filtration starting from the maximal minors, from the variety of the maximal minors, right? So, and in fact, all this singularity theory is, in some sense, concentrate on the maximal minor, but as a consequence, we get information for all the other minors because of this filtration that we have, and the group preserves rank, right? Leaves invariant the strata. Okay. Okay. So this is just a quick example to show how to construct the unfolding, right? So we have the singularity from an Frieb's and Neumann list. We computed the tangent space. I don't know if we can use Oscar to compute the tangent space, but maybe Matthias, more or less. Yeah, okay. So we computed the tangent space and the normal space. So the generators of a normal slice. And we can then write the expression of this stable unfolding, which is here, right? So this term Zi, I varying from 0 to k minus 1, in this position here, gives the normal directions, the transversal directions to the germ. So this is, again, Cohen-Macaulay codimension 2 is a surface in C4, right? Okay. Unfoldings are uniquely determined up to diffeomorphism in the category of unfoldings, right? So if you have a map F, which is G-finitely determined, you have uniquely defined the unfolding of this map. And this result is really fundamental so that we can explain that we have a singular vibration associated to F. So suppose that you have then F from Cn to Cm cross n, and x0 is F inverse of mnt. So we have here an EIDS in Cn. And since it's an EIDS, since F is G-finitely determined, we can take its stable unfolding, which is a map parameterized by S parameters, where S is the codimension. So F tilde is the stable unfolding. This stable unfolding define, well, of course, it's an unfolding of F, so F tilde of x0 is f of x. This unfolding define the variety x tilde F2 inverse of sigma t, right? And by property of the unfolding, it's transverse to the rank stratification, right? So we have then a diagram. So we have this big determinantal singularity, which is also an EIDS, living in Cn cross Cs, right? And this is the projection to the parameter space, like similar to what we did in the case of ICES, right? But in the case of ICES, this big object here was smooth, right? Now, not anymore. But then here in the parameter space, we have the bifurcation set. Before we say what's the bifurcation set, let's look at the fibers of this projection under the fibers in X under this projection. So of course, the special fiber pi inverse of 0 is X. And pi inverse of another parameter u here is another determinantal variety, which may have singularities in X, right? And for generic value of the parameter, Fu, F tilde u certainly is transverse to the stratification. And hence for generic values of the parameters, the fiber is an essential smoothing of X. It's, so to say, stable, right? The bifurcation set is the set of values in the space of parameter such that the fiber is not an essential smoothing. We can verify that the set is an analytic set. And so its complement in CS is connected, which means that if I take any value of the parameter outside the bifurcation set, the fiber is an essential smooth. This is what I said, is a proper analytic subset. And then for any value in the complement of the bifurcation set, F tilde U define determinant override X tilde U, which is an essential smoothing of X. As I said, this procedure is well defined in such a way that because this set is a connected set, any U in the complement of the bifurcation set gives a fiber X2U, which is well defined from the viewpoint, from the topological viewpoint, right? So the complement of the bifurcation set is an Zariski open set. So any two fibers corresponding to points in this set are topologically equivalent. So this is the most important information of this lecture, because in fact, going through this approach of looking at the landscape of singularity, we get here a well-defined object, which we can call determinantal Müller fiber, for instance. It's singular, but its topological type is associated in a unique way to the IDS. You can find more details in order to verify that this projection here is defines a fiber bundle outside the bifurcation set in Matthias' thesis. Okay, so just to finish, because my time is finished now. Okay, so then we, just to say that invariants of this fiber, topological invariants of this fiber are topological invariants important to study EIDS. And I remember two of them. One is the Euler, reduced Euler characteristic of the determinantal fiber. And the other one is the polar multiplicity MD. I think Terry will define this invariant, right? And I'm sure that Matthias and Jim will discuss a lot the topology of the determinantal Müller fiber, okay? It's okay, because my time is over. Are there any questions?
Could you come back for a moment to the definition of the tangent space? Because I didn't understand it, the right-hand side. The two matrices C and I and R, I think they were. Okay.
Okay. You didn't understand this side?
Yeah. Those two matrices are any two matrices of the form that you said, no?
Given F, the
Okay.
map F defines you a matrix, right? Gives you a matrix M by N. And so for that matrix, right,
Okay.
you define this matrix L, RL and Cij, just replacing the L's column row by the case and putting 0 in all other entries.
Okay, they depend on F. Okay.
Yeah.
Thank you.
This microphone.
Maybe I can quickly comment on that.
Yeah, sure.
Another way to interpret this is that you multiply from the left and the right with invertible matrices, and when you take infinitesimal deformations, or when you take the derivative in an appropriate sense, then this comes out that you get some perturbation. So it's related to what we discussed yesterday briefly at the blackboard.
Do you have any results about linear EIDS when you apply this machinery to them?
This is a nice question because, well, we were working on this, right? And of course, we can obtain, how can we obtain linear EIDS? For instance, we can obtain linear EIDS taking linear hyperplane sections of the generic determinantal varieties, right? And so we can get, and we got some nice properties about linear EIDS, right? But one open question is, of course, we expect that generically this will be EIDS. Of course, they will be EIDS. So generic hyperplane section intersects transversally all strata away from the origin. But the interesting question is to give a normal form, given a matrix type, M and T, how can you exhibit a normal form of linear EIDS? This I don't know how to answer. Not yet. Yes, Juan? Terry?
So just a comment about the fact that for determinantal variety, you might have different matrix representations. So my comment is that you have to think of a determinantal variety as a variety with an extra structure. So you might think that the determinantal variety is a pair when you have one variety and one matrix representation. Because most of the invariants that you define, they depend on this choice of the matrix representation. So for me, a determinantal variety is a pair when you have a variety and a matrix representation.
Sure, but this, I think we explained this in the first lecture, right? But it's interesting what you said, and maybe we should look at the Pimpham's example, and if possible, in our exercise session, to see what. But this is what one thing that we said as one main reason, in fact, to take this approach, right?
Do you know something about the stratification of the bifurcation set depending on the G equivalence, by G equivalence?
Well, it's a good question. For our exercise class, I hope to do one example, right? For that surface CC4 that I gave as first example. But I don't know how to give you a general answer. Do someone know?
There will be some discussion of this in my lectures, I think. And yeah, it has quite some interesting structures, but you will have to wait until Thursday.
Okay. Okay. Thank you. So again, we are late. I'm sorry. So 5 minutes, right? Sure.
Just to be sure, you said this geometric criterion says that if the map is finally determined, then you have an EIDS, or did I miss some condition?
quick test. Here's the test. Okay.
Hi, Matthias. Matthias? Do you
You're
hear me?
already there. Yes, I don't
Yes.
I don't see you.
I suggest that we start with the small leftovers of yesterday and then jump into slides set 4 and worksheet 4. So we start with slide set 3 and worksheet 3, the rest.
Yeah, okay. Ah, there you are. Hello.
Yeah. Hi.
Yeah, I have worksheet 3 open at the point where we left yesterday.
Yeah, basically it's just the conductor and delta that are
Okay,
left.
so should we start? I mean, probably not everyone is there. Let me quickly say that that we're starting. So I think it's okay. Welcome back, everybody, after this short break. It's okay, right? And yeah, still some people coming. So Anne, do you want to summarize where we left off yesterday?
Yes, that's where I wanted to start. Yesterday we talked about computing normalization, and we had the whole algorithm on the slides and also parts of the algorithm on the worksheet. Now, the situation is we know that we can compute a normalization, that is the integral closure of a ring in its field of fractions. And we know that we can write it as a subring of its normalization. Moreover, by a result of Noether, if our ring is a polynomial ring modulo a prime ideal, then the normalization will be finite over the ring A. Since it's finite over the ring A, we can ask what are the elements we can multiply with so that whatever is in A bar ends up in A. So we can ask for the annihilator of A bar mod A, the A annihilator. And that can be computed, of course. Actually, the non-normal locus of A is precisely the support of the annihilator, that is, it consists of those points where the annihilator is not the whole ring. So we have a way to compute the non-normal locus a posteriori, because of course it needs the normalization. And there's another important invariant. It's the k vector space dimension of A bar modulo A, which is called the delta invariant. It comes up as the virtual number of double points for curves. And here I have an example for you so that you see what's going on. So we start, say, with a curve in 3 space given by those 3 equations. So it's not a complete intersection. And we know from computation of normalization that this coordinate ring is isomorphic to the ring C adjoint T to the 4, T to the 5, T to the 7, seen as a subring of the normalization C adjoint T. So let us mark all powers of T that are in C adjoint T4, T5, T7 inside the set of monomials of C of T. Set of monomials of C of T is, of course, on that line here. And we have T to the 0, which is in both rings. T to the first to T to the third is not in the smaller ring, but T to the fourth. I marked it in red, and all multiples of T of the fourth are here. t to the 8, t to the 12, and so on. We also have t to the 5, and that, of course, brings with it its double t to the, so it's second power t to the 10, and so on, but also the mixed product t to the 9, t to the 13, and so on. And we have t to the 7. T to the 7 brings us t to the 14, but it also brings us t to the 11 if we pair it with t to the 4. So from t to the 7 on, all monomials of CFT are also in the smaller ring, but below that, this is not the case. So our conductor ideal is actually generated by t to the 7. It need not be the largest generator that we have up there, but in this case, it is. And we can also look at the number of holes, 1, 2, 3, and then 1 at t to the 6, so it's 4 holes. The delta invariant is 4. So here, usually if you compute the delta invariant in this way, it's just a semi-group computation. Now, to end this topic of normalization, let me just briefly make a few remarks on Serre's normality criterion. For that, we need the notion of the height of a prime ideal, which is nothing but the dimension of A localized at the prime ideal. And then Serre's criterion says a reduced Noetherian ring A is normal if and only if it is regular at primes of height 1, and if and only if for every non-zero divisor, the minimal associated primes to the principal ideal are already all associated primes to that principal ideal. So in other words, the criterion says we need regularity in codimension 1, so the singular set needs to have codimension at least 2, and we have the criterion S2. That brings me to a warning. Normal varieties may be singular. They may be even highly singular if you are in high dimensions. It's just a peculiarity of curves that normal curves are non-singular, because in curves, our low dimension 1 doesn't allow us any singularities in codimension 2. So, for example, the cone xy minus z squared in A3 is normal, but obviously it has a singularity. It has an A1 singularity at the origin. So this is what were the leftovers of yesterday, and we still have some leftovers on Matthias's worksheet. So I now give the word to Matthias.
All right. Let's bring the worksheet up. I think I need to zoom in a little bit. So where were we yesterday? We did a normalization of a quotient algebra. Let's wait a little for the normalization to come up. Yes, there we go. And we saw a little bit how you can read off this parameterization of curves also by investigating the output of the normalization. For instance, this curve was parameterized by t to the 3 and t to the t squared. That was the cusp. And you can also repeat the same thing with other curve terms which are not necessarily reduced, which are not necessarily irreducible. For instance, here you see in the first equation x squared minus y fourth decomposes in the product. So what do we get in this case? We get another parameterization, and as it seems, 2 parameters, but here are 2 branches. I mean, the ideal that defines our normalization upstairs. After we simplify it, we get two branches depending on T1 being either +1 or -1. And then, as it seems, y is this parameter on both branches. Good. What else did we have on the slides? I think this is the other curve. Anne, is this the curve that you just showed?
No, that's a different curve.
That's
I think that's the one where we have to find the number of branches. That's a warning about working over Q and thinking over the complex numbers.
Yes. Is it already time for that example?
Yes.
Good. So here sorry?
Go on.
Yeah, here we have a space curve, right? Before we had a cusp and another singularity in the plane. Here we have three variables and a rather complicated ideal, which has three generators again, as you can see here. So first thing to check is, do we really have a curve? So what I did was a primary decomposition, and then I also give you the dimension of every component that comes out. So what is this? What is the result of the primary decomposition? It's not so nicely readable, but well, you have two components, and both of them have dimension 1. So indeed, we do have a curve. We have a curve which over Q decomposes into two components. But we already saw in the exercises last week that we cannot rely on 2 being really the number of geometric components, because if we pass to a field extension, they might decompose further. And normalization is a way to parameterize branches of a curve. So in this case, in particular, we will see that the normalization takes care of separating the branches. How does it do it? Well, let's first set up the quotient ring for this ideal. We call it A again. So the polynomial ring in XYZ modulo the ideal upstairs. And we compute the normalization in the second row. And as we saw before, the normalization has a rather complicated output, but the first thing that it gives us from the whole list, it is the quotient ring for what's upstairs. And we can again call this Elimpart routine, this Swiss knife to open every tin. And then we can stare at what it tells us and try to guess how to interpret it. So as it seems, the normalization did not only introduce one more parameter, but it introduced 4, right? This is what you saw yesterday on the slides, but here now you see it in action. So T1 to the up to the T4 are the parameters for the normalization, the newly introduced parameters. And what Elimpart says is we actually only need 2. The others we can solve for the others from the ideal. And we can solve like this, right? T1 is T4 to the 4th, and so on and so on. And only for T4 and Z, we cannot solve. And the ideal in the ring with variables T4 and Z, after all this substitution, it has still an ideal, and it's T4 to the 5th minus 1. So it's about the 5th root of unity that separate our branches. And then we also need a parameter, and the parameter is Z. Right? So the picture, if you wanted to draw a picture of this situation, then maybe down here you have a rather complicated curve. And then upstairs, the picture looks nicer. 1, 2, 3, 4, 5. You have the singular point downstairs and 5 pre-images. And this is the T4 axis. And then down here, you have the Y direction. And outside this exceptional locus, the map downstairs is 1-to-1 on every branch. Questions? Good. Anne, anything you want to add?
No, you beautifully explained it. And I just want to add the warning that here we had 2 components over the rationals, but we have 5 components over the complex numbers. And therefore, be careful if you do something like factorization or primary decomposition while computing over the rationals, what you are forced to do on the computer. Sometimes you have to amend for those problems by doing suitable field extensions, like here, a field extension with the 5th roots of unity.
Right. As you saw in the exercise sessions already, right? And in Oscar, you can actually try to adjoin this 5th root of unity and make the primary decomposition work. So now comes this delta invariant that you saw. Unfortunately, I have not produced any code that does the proper monomial counting for you or prints the monomial diagrams. But I would just want to say that it can be computed. For instance, in this example, I think you had slightly different exponents here, right, Anne?
Yes, I had a 7. That's the second example.
Okay.
You have it just one line further down.
Good. Let me briefly explain what happens here. Here we start from the other way around. Before, we started with an ideal and we wanted to parameterize that variety. Now we're cheating. We start with a parameterization and then produce the ideal, right? So how do we do that? We set up 2 rings, R and S, and here is this homomorphism, the algebraic homomorphism, ring homomorphism, which on the geometric side is this parameterization. And we saw in the beginning of last lecture that we can use elimination orderings to compute the ideal for the image. And fortunately, you don't have to do this by hand. I mean, we're doing this in the course for you to learn how to use elimination orderings. But of course, there are more convenient ways to do that. And that is just computing the kernel of this ring homomorphism, phi. And then a posteriori, we can ask for the delta invariant of the singularity. So let's see what the outcome is. Oh, simple. Okay, and that should agree with what we have on the slides, right?
Exactly. And now I would suggest that we jump directly into talk 4 to save some time, because we already ate up a quarter of an hour, I think.
All right. So in the worksheet, you will also find some quick remarks on the normalization of higher dimensional varieties, but let's go ahead. So will you take over with your slides first?
Yes.
Good.
And we heard something about unfoldings already this morning. Let me just briefly get notation straight. So we are talking about an unfolding of a power series if we have a family of power series in new variables, t as parameters, such that for t equals 0, we have the original power series as our f of x and 0. Now, such an unfolding or perturbation of a power series induces deformation of our hypersurface. And for the time being, I'll focus on hypersurfaces. I'll come back to the general case on later slides. But for the moment, let me introduce the notation for hypersurfaces, a deformation is a commutative diagram where you have down here S0, the germ of your base of the family. So that's where your T's come from. You have your fiber above 0 here as x0, and you have your total space at the curly x. And the map from curly x0 to S0 should be flat. We'll come back to the flatness later on. For hypersurfaces, it doesn't make sense to talk about that because that's automatic here. Now, in pictures, I've just perturbed an A4 singularity and wrote down the perturbation here. And then I look at 3 fibers, fiber at t equals -1, t equals 0, and t equals 1. And you see, we see different singularities here. So for t equals -1 and t equals 1, if you know the classification, you'll see A2 singularities. And for the fiber at 0, you see an A4. Given such a family, we can ask, is the family trivial? What singularities appear in the family? Is the general fiber smooth? So for the family we had on the previous slide, of course the family is not trivial because we see different singularities. But the only singularities that we see appear there are A4 and A2 for that given family. And of course the general fiber is not smooth because for that family, the simplest kind of singularity we see is an A2. On the other hand, we can pick a central fiber, we can pick a singularity and ask what singularities can appear in families that have this singularity as the central fiber. We can ask how many different types of singularities can appear in families having this central fiber. And last but not least, we can say, if we have a family with this central fiber, can we induce any possible family from that family we have? That is a question for causality. So there are many questions you can ask to deformations of singularities, and we'll give you some hints on answering parts of them here. So of course, you know, right equivalence is equivalence up to coordinate changes in the origin, and contact equivalence is equivalence of space germs. Those are the most commonly used equivalences for hypersurfaces. And I'm sure last week you saw at some point finite determinacy. A power series is finitely determined if there is some natural number k such that two power series coinciding up to k, that is a power series G coinciding with F up to order k, already implies that the two of them are equivalent with respect to the respective equivalence in question. Now, there's a very easy shortcut to check whether something is finitely determined and even get a rough bound for determinacy. Just compute its Milnor or Turiner number. Milnor number for the right equivalence, Turiner number for the contact equivalence. But those bounds, mu plus 1 and tau plus 1, are usually rather far too high. So we should use beta criteria, and of course there are beta criteria, but they are not just numbers, but they are things to check. Here, with a simple ideal membership test as is provided by standard basis computations, we can check whether F is right k determined, namely if the k plus first power of the maximal ideal is contained in m squared times the Jacobian ideal, and the same for contact equivalence. Of course, it looks the same, except that we have to take into account also the additional generator F with the factor m up front. No, we won't have that on the slides today. That is an exercise for you for the hands-on session tomorrow. Write a function which takes F and k as input and checks the above condition for right determinacy or for contact determinacy, however you want, returning true or false. So that's an exercise I put in here. And now back to deformations. A deformation, and now I haven't written the commutative square, I've just written the vital information, that is the map in the upper row and in the right-hand column. So a deformation of that kind is called Wurzel if any other deformation over a different base, but with the same special fiber, arises from it by some base change, that is induced by some map from the new base to the old base. And a task that we want to do is find a Wurzel family for a given special fiber. For hypersurface singularities, that's not too difficult, and because of the time constraints, I'm now going fast, and I assume that you saw it in lectures before in that school. We compute a K vector space basis, K being the ground field, of our T1. Remember, for hypersurfaces, the T1 is a Turing algebra. And then we set our perturbed power series to be F plus the sum over the TIGI, where of course I runs to from 1 to tau, because the GI are just the generators of our T1 as a K vector space. And then this perturbed power series just defines our Wurzel family curly X. So we know we have all the tools to do that, and we can do that computationally. But given such a Wurzel family, you can also ask, what fibers of the family are singular? And to do that, you want to treat the T variables as parameters and the X variables as variables. That is to say, you don't want to apply coordinate changes to the T's, so you will, oh, that should be capital F everywhere in that line, sorry. That should be capital F wherever there's a small f here. So you only factor out f and the partial derivatives by the x variables, but not by the y variables. This gives you the relative T1, and then the discriminant is the intersection of what you factor out up here with the smaller ring only involving the T. Please bear in mind, if you have many variables, if you have a high Turing number, then elimination will be a very expensive standard basis computation, because standard bases are doubly exponential in the number of variables. So now it's your turn, Matthias.
I prepared some Wurzel deformation, but not up to contact equivalence, but right equivalence, which means up to change of coordinates in the domain of the function. And you may all know this, but let's see it again, and especially let's see how you can really program it, because this is something that gets tedious to do by hand, and the computer can help you a lot, I think. So we start with the A3 hypersurface singularity. Oh no, sorry.
A2.
I forgot to correct this exponent here.
Oh, okay. Yep.
I think
makes sense.
It's 4, right?
Yep.
So this is a surface singularity, and we can compute the singular locus and try to capture the Milnor algebra, right? The Milnor algebra plays the role of this Turing module for right equivalence. And we saw this before. We can compute the leading ideal of that ideal and then count monomials. And eventually we find that the monomials 1, x, and x squared, they are a basis. They reduce to a vector space basis for the quotient for this Milnor algebra. So the high arts are to find to program a function that does this monomial counting for you. And I brought you one here. I don't want to go through all the details, but I think for you it's very helpful to have sample code, right? If you don't know the programming language and you want to learn from somewhere, it's always good to have some point to start. So this will be uploaded, and if you have questions on what's happening, ask me. I'll be happy to answer it. So we can define this function, and then hopefully it gives us the right thing. Yes, we're lucky. Right, so all these tedious computations by hand, once you know how they work, you can also give them to the computer. And then you can even write another function that writes down the semi-universal deformation. So here maybe I should comment, because otherwise it's difficult to follow. We have the ring for the original singularity in the variables x, y, and z. And we need a new ring which also introduces the deformation parameters. In this case, u1, u2, and so on. And that is done here. It's not even fully visible. So basically what it does is it makes a copy of the old variables. But in the machine, it's also important to distinguish them, that they are distinguished, right? They live in two separate rings. It's only you as a programmer who understands that they somehow have to be identified. So the old variables and the new ones, the parameters, and then it assembles the function according to the formula that you saw on the slides. And it returns, again, quite a lot of information. First one is the capital F that defines the total space of your unfolding. And then maybe we also want to have the information which ones of the variables are variables and which ones are parameters, right? So you also return the variables and the parameters. That's not spelled out here, but that's what happens. So when we apply this, we get this output. So you see a little unordered the hypersurface for the semi-universal unfolding with the parameters u1, u2, u3. And this is the set of variables, and the second is the set of parameters. Good. And Anne, do we want to go here straight away to compute the
Yes,
discriminant?
I did the discriminant on the slide, so we can go there and also show how to do classification.
Sorry, I did not fully understand. Can you repeat that?
I said, yes, we want to go there. I did the discriminant for a hypersurface singularity already on the slide. So we can do this. We jump part of the functions, just say what they are doing, and then go to the classification also.
Okay, so the task is to compute the discriminant of such an unfolding, right? So you have, well, when I mark this, it doesn't become more readable. So I let go of it. This has all been on the slides, really, yes. So a crucial point is that we need this relative Jacobi matrix, right? That was also on the slides. And we need to do a new method, because if we just ask for the Jacobi matrix of the capital F, then it will also take derivatives with respect to our parameters. And again, this is a function. I program it. If you have a look later when you want to do something yourself and there's something you don't understand, ask me.
But of course, there's always the other possibility to take the whole Jacobian matrix and then pick an appropriate submatrix, as we saw it at the first worksheet. That's the alternative.
That's another possibility. But here, this would be the Julia version of solving things for the expert. So here now comes the manual discriminant computation according to what we saw in last lecture. We take this relative Jacobian matrix, we take minors of this, we also need to add the hypersurface itself, then to the ideal, then we choose an elimination ordering in the variables to project to the parameter space. We compute a standard basis and we collect those equations that do not involve any of the original variables anymore. And those of us who also remember the first 100 digits of pi, maybe they also recognize this equation straight away. Right? It's a discriminant for a depressed polynomial of degree 4. It's a very well-known polynomial in 3 variables.
You could also say it's a very well-known singularity. It's a swallowtail.
Right. This is the other interpretation. Yeah. So it's a swallowtail for those who work with it. So should we go ahead or?
Yeah.
Yeah. Okay.
We go straight through, but before you get to complete intersections, I take over again with the slides.
Good. So you may all know the swallowtail. If anybody knows how to draw it, please do so. Come forward and assist me. But what we can do is we can investigate the singular locus of the swallowtail, right? So the discriminant has very special geometry and has non-isolated singularities. So algebraically, we see that here we have 2 components of the singular loci. So we have a smooth stratum of this swallowtail and 2 singular curves, and this should correspond to the fibers being singular in different ways. Thank you. Right, so the 2 components that we saw in the primary decomposition, I think they should be this and the other one this. Is that correct?
Yes.
Good. Because it's rather hard to read from the output, we choose some points. Right. So let me try to find these points also in the picture, but please stay on with the presentation, stay on the, anyway. So T1 should be in the regular locus. So imagine T1 is somewhere here. T2 and T3 are then one somewhere here and the other one somewhere here. Here, I'm not so sure. Maybe they have to be interchanged. But it's only a picture, right? So that's how you look at it. So let's check whether this is really the case. So T1 is on the discriminant. That's what the first output says here. Yes, okay. This one says it's neither on the first nor on the second component. We can do the same again here with T2. Well, it is on the first component, but not on the second of the singular locus. And T3, it is not on the first, but on the second. Good. And then we can try to make the singular loci of the swallowtail correspond to the singularities that we have in the family upstairs. And how do we do that? Well, we need to get the function that defines the fiber. And we do that simply by evaluating.
Matthias?
Yes?
I got the message from the technician that the time is up. Could you just go to one classification and we call it a day at that point because they want us to stop here?
Good. Let's take this point. There we go. We have one singularity, which is not at the origin, and we want to use this classify command, which can only compute singularities at the origin. So we have to apply first shift, and then we can classify. And classify tells us this fiber has an A2 singularity. And I will upload this worksheet. You can play around with it, discover components of the swallowtail, etc. And if you have questions about that,
And
feel free
there's
to
one
approach.
thing we should really get to that's down there in the complete intersection part. Can you scroll down quite a bit?
Yes.
Stop somewhere here. There you get information on how to handle modules. That's on that worksheet. So because for hypersurfaces you can do everything in the ideal theoretic way, we mostly used ideals and not modules, but you will need modules if you want to do ICEs or more general singularities. And on the worksheet, where we didn't get to because we didn't have the time, you find the information on how to handle this with modules, and also the pitfall that an ideal is not a submodule of a free module of rank 1, but just an ideal and has to be transformed into a submodule of a free module of rank 1.
Yeah, I think we can pick up on this in the hands-on session also. Maybe this is
Yes.
even better because then you can directly work with it.
Oh, I got the information. Don't rush, take your time. But I think it's still the point where we should say, sorry, we couldn't fit in anything else here.
All right, so we finish at this point.
Yeah, I think we have to finish at that point. We could easily have filled another lecture.
Okay, thank you very much.
And thank you, Paolo and Leonardo, for your technical support. Without that, we couldn't have done this in a hybrid way.
Yeah, thanks to the technicians. Once time. Okay, I see we still have questions. One question.
Okay, so is it possible to compute the bifurcation set not for C equivalence of functions with isolated singularity, but for right equivalence? So the bifurcation set is the set of parameters when you don't have a Morse singularity or where you have several Morse points with the same value. So this, generally, this is not easy to compute.
I see. I would say there must be a way to do that, but I don't have an algorithm that comes directly to mind. That's true. Anne, do you know?
I don't see anything directly, but we could meet in a video conf and talk about it more.
So I think this will be something that people want to have. So we should have it.
Okay.
Anything else?
Maybe I missed it, but to compute the Turin number, I'm sorry, to compute the delta invariant, did you suppose that the curve is reduced or it may have a fat point?
No, we had a reduced curve there. Because the function for Hamburger-Noether development that's in the background that was used there for the delta invariant only takes reduced input.
Sure.
Good. More questions? All right. That does not seem to be the case. So thanks again for attending. Have a nice break and see you in the next session.
Can you hear me? Yeah, I think yeah. Good morning. So I think we can start, right? So I continue the course on Lipschitz geometry of singularities. Today I will talk about tangent cones. I will define it. I will list some good properties, and also I will prove that the Lipschitz invariance of the tangent cones. So let me start define what means tangent cone. In fact, I will define in a different way in a different way of that definition given by Alexandre, but in the middle of this lecture, I will show that these two definitions are equivalent. So let me define, for example, let X in Rn be a set, and let P and P a point in the closure of X. So we say that V in Rn is a tangent vector of X at P if there are sequence xj in X and tj in the positive part of R, such that we have this, the limit of xj minus p divided by tj is v. And in this case, we collect all these, let C of xp, oops, be the collection of all tangent vectors of X at P. And this guy I will call the tangent vector, the tangent cone of X at P. Okay? So let me give some examples of that, which is the tangent vector, tangent cone of a set. For example, let me examples. For example, A. If you take the cusp, let me call the cusp x, y in C2, for example, such that y square is equal to x cubed. The tangent vector of x at 0, for example, is just y equal to 0. We can do in an easy way these calculations. I will not do that. In fact, this comes from a more general property. In fact, if you have x, for example, let me put B. If x is the zero set of some analytic function, f from Cn to C analytic. And for example, if you write f has something like that, fk plus fk plus 1, sat, where fj is homogeneous, right? Of degree k, of degree j, and of course k is the mean of such k's, of such j's, and if k is different to 0, and then the tangent cone of x at 0, for example, is the zero set of fk. And of course, if you know this is true, it's easy to obtain the item. Yep.
In the complex case, so you consider Cn are as R2n.
Yep.
Simply.
Yep.
So the Tj are real numbers, not complex.
Yeah, real numbers. Yes, that's the point. In fact, we can show, for example, in the complex case, even if you take complex numbers, you obtain the same set. Of course, if you take complex numbers different to 0, for example. These are good exercise, for example, to do that. In fact, if you define in the same way this, you put this definition for complex analytic sets, but allowing the sequence Tj to be some complex number different to 0, we can prove the same characterization in the middle of this lecture. And from that characterization that I will prove, we can prove, for example, the definition allowing Tj complex numbers is the same allowing only positive real numbers, for example. So, in fact, this comes from even a more general property. Maybe the people who knows about complex analytic geometry knows, in fact, if you, for example, has now a set given by a finite number of analytic functions. For example, let me put C here. For example, if X now is the zero set of some ideal, okay, some ideal of an ideal in ON, for example. This notation, I think, is already used in some lectures before this one. And for example, if I define I star has some, let me, for example, define this polynomial has the initial part of f. Let me denote, for example, I will define something like that. Fk is, I will denote like has initial part of f, something like that. This will, so I put, with that definition, I can define this way. Let me, this is the ideal generated by all the initial parts of the functions in the ideal I. Okay, so the tangent cone of X, we can prove, for example, this is the zero sets of I star. And this is why we know, for example, the tangent cone of an analytic set, complex analytic set, is an algebraic set. Okay. In fact, it's more than an algebraic set. It's a homogeneous algebraic set. That means it's given by homogeneous polynomials. Okay. Zeros of the homogeneous polynomials. You can find a proof of that in the Shika book or the Whitney book, complex analytic sets and complex analytic varieties. I will not prove that, but I want to remark, for example, this kind of result only hold in the complex setting. For example, let me put D, the example already given by Alexandre Fernandes yesterday. He showed, for example, the tangent cone effects is now the cusp, but the real cusp. Then the tangent cone of x at 0 is just the part of x 0, but x greater than 0. Okay. The picture is something like that, right? So the cusp is something like that, and the tangent cone, I cannot draw a line. This is why I'm not doing pictures, because I cannot even draw a line. But the tangent cone is that, right? This is the tangent cone. Okay. So, unsaid these examples, let me list some good properties of tangent cones. Many of them are very easy to prove. Maybe I will select some of them to give hints in the class of exercise today afternoon. Okay, so let me list some properties. For example, we have monotonicity. That means if you have a subset of x, this implies the tangent cone of A is contained in the tangent cone of X. You have additivity. That means if you have the tangent cone of X union Y at P, this is the tangent cone of X at P union the tangent cone of Y at P. However, we don't have good properties to intersection. For example, we only have the tangent cone of intersection at P is contained in the tangent cone of X at P intersection the tangent cone of Y at P. An example can be given where we don't have the equality here. For example, we can consider in this example just this example. For example, we can prove, for example, even if you consider X only the upside part of this picture, and Y this orange part, both of them have the same tangent cone, even this green part. the intersection is only the origin, but the intersection of the tangent cones is the tangent cone. So we don't have equality here in that example. For example, we have for property, the definition of tangent cones has good properties to product of Cartesian product of sets. That means if you take the product of x and y and at some point P and Q, this is the tangent cone of x times the tangent cone of y. Like in the notes, there is a type here. Here appear in the notes P, but it's Q. Let me remind more properties. Yeah, these are generalization of tangent cones, the tangent space from the differential geometry. That means if X is a C1 submanifold of Rn, then the tangent cone of X is equal to the tangent space of X, of course, for P in X. Okay, and also this is everything follows in an easy way because it just apply the definition. You can obtain the four first properties. This fifth one maybe it's not so directly, but in fact it follows from the sixth property. The sixth property is easy to prove also. If you have a map from Rn to Rp, let me put P and Q, Rn, for example, which is differentiable at P. And then if you take n set X in Rn, the tangent cone of phi of X. Sorry, that's not here. Sorry. The tangent cone, the image of the tangent cone at P of the set X at P is contained in the tangent cone of phi X at Q. Okay. So if you have, for example, phi being a diffeomorphism, like if it's given by if it's a chart, for example, it's easy to prove. For example, the tangent cone of Rn is Rn. Then the image of if it's a diffeomorphism, this is a equality, and then the image of a linear space is a linear space, and it's more or less follows from this property. The fifth one follows from this one. Okay, I want to say another one, just the last one. In fact, the numbers are not the same anymore. The tangent cone is a real cone. that means if it's a real cone. If you take a point in the tangent cone, and if that means if V is in the tangent cone, then lambda times V is also in the tangent cone for n lambda greater than 0, for example. And of course, it's easy also, the tangent cone of a real cone is the real cone, of course, at the vertex. Okay, the tangent cone of a real cone at the vertex is the real cone. So, unsaid that, I want to add an exercise that I forgot to put in the list. I will state here just to feel the power of this tool. In fact, for me, in my opinion, this object is the most important object of Lipschitz geometry. And let me put an exercise here that can give some idea of how powerful is this tool. For example, exercise. In fact, the tangent cone can help you to decide if a set is smooth or not. For example, of course, if the tangent cone is not a plane, it's not smooth. But we can obtain, for example, the case the tangent cone is a plane, but it's not smooth also. But the tangent cone can give, for example, let me write what I want to say. Let X in Cn be an analytic set. Analytic set. Okay. So we have the following equivalence. X is, let me put the origin, is smooth at 0. At 0 in X, okay? If and only if for some projection, let me put P from Cn to CD, D is the dimension of X, such that the kernel of the, I will continue there, I think I will continue here, okay? I have space here, okay? Oops, or not. It's very, I can, something. Let me continue. If and only if there is some pi such that the kernel of pi intersect with the tangent cone is only the origin, and for some polydisk delta in R in Cn, we have the following: the cardinality of the Prey measure of T in time intersected with X intersected with let me write in this way: delta prime time delta prime prime. In such a way, we are projecting in delta prime. Okay. Cn. This is one for a generic T in delta prime, for example. if you, for example, can obtain some projection that satisfies that kind of coordinate, that kind of transversality. This, in fact, is a transversality condition, and such that the pre-image is almost in every point has only one pre-image, for example, only one point. Then the set is smooth. In fact, you can prove if there if it's true for some, it's true for any projections that satisfy that kind of condition. Because if you can prove this one, if it's smooth, of course, the second condition is true for any projection. Because we have, in the smooth case, we have implicit function theorem. Okay? So, I think I want to state my the result of characterization. I think it's time. Up to now, any question, right? Okay, so I think I almost forgot this, the last one. I have one more way to present tangent cone. Let me present that. I have time. Let me present that condition. For example, if you now one more way to present tangent cone, if let now x in Rn, for example, and let rho from Sn minus 1 times 0 plus infinity to Rn, the map that sends x t to t times x. Okay? And now we consider x prime to be the pre-image of x minus 0, and then we take the closure. And then we can define the boundary of x prime just the part of x prime that lives in the bottom. And then we can prove this is just the tangent cone of x times 0 intersect with the sphere. So this object is important. For example, we can more or less can keep information of the set x and the tangent cone in the same object, x prime. We call this guy the strict transform with respect to this map rho, and also we call this map rho the Blow spherical blowing up. Spherical blowing up, sorry. We call this map spherical blowing up, and this is the strict transform, and this is the divisor of that strict transform. It's more or less something like that. Let me draw some example. In fact, two examples. These examples because if you are in that case the cusp, if you are in the cusp case, you're in the cusp case, and then you want to do this is rho, And then this is something like that. We transform the cusp in something like the parabola after one blowing up. And if you had another kind of example, something like that, a line, this is transformed in something like that. A line here and a line upside. We divide in two sets because they measure the tangent cone. So this is one direction. The tangent cone of this set is here. It's the link of the tangent cone. The link of the tangent cone. We have to divide. This is more or less what happened. So we can, by local structure theorem, conical structure theorem, this guy has the same topology of the link, the homotop type of the link. And of course, we can recover the topology of X from the link. So in some sense, we have outside of the origin, this guy is a diffeomorphism. Okay, for outside of the origin and outside of Sn minus 1 times 0. And so if you don't put if you don't take the closure, you have something like diffeomorph to X minus the origin. And when you take the closure, you obtain the link of the tangent cone. So the link has all the topological properties that you want of the tangent cone. Yeah, if X is subanalytic, the X prime is a subanalytic. But I'm not assuming that. This holds true even in generic case. Yeah, in set. And for
For the so the last sphere, do you need to take the product with the 0 point or something?
Okay,
No?
here.
Yes. No.
No. Yeah, that's the. No, that's the. I wrote it in the wrong way. Sorry. This is what I want to say.
Okay.
This is what I have dyslexia, so I do. Thank you. Okay. Just the link of the tangent cone times 0. Is what I was saying. Okay. So this is another way to present tangent cone, because after that you can take the cone over this guy and you recover the tangent cone. Cone means all the half lines passing through the points of this guy with vertex at the origin. Alexander will use this definition for prove a nice result about invariance of relative multiplicities. Okay, so now I will state the characterization. I think we have to do a break in 10 minutes, I think. I don't know if I think I will have time to prove that proposition. So now I assume X is subanalytic. Okay. If you don't know what means subanalytic, imagine X being a semi-algebraic set given by inequalities and equalities of polynomials. Okay. Let X in Rn be a subanalytic set. and P in X minus P, a non-isolated point of X. Okay, that means I want that there is at least one sequence of points in X converging to P, for example, different of P, different from P. Okay, so are equivalents. The following statements. I will just say then V in Rn is a tangent vector of X at P if and only if there is a C0 subanalytic arc gamma from 0 to epsilon to the closure of X, such that the image of the 0 epsilon is in X, and gamma T can be written in the following way. And this means when you divide by T, the limit is 0 when T goes to 0. Okay. In fact, it's easy to obtain C1, but C1 is the best regularity that you can expect there. Okay. C1 alpha for some alpha holds, but we cannot obtain, for example, C2 in general. Okay, so the converse part is easy, right? Because you can, for example, define Tj to be epsilon of j plus 2, for example, and xj to be gamma of Tj. And of course, when you divide, I was assuming the point was 0, but no. The point is minus P is, okay? Sorry. If P is 0, that's true, but gamma of course, I'm assuming that this is also a continuous function. So gamma of 0 is P. Okay. Gamma 0 is P, gamma of 0 is P, and then also the converse is easy. You just take, if there exists some gamma, we choose Tj and xj some like that, and this implies xj minus P over Tj goes to V. So V is a tangent vector. Okay, so it's the hard part is the implication. The implication, if there is some sequence, if the tangent vector, if V is a tangent vector, there is some sequence xj and Tj satisfying something like that. So we have to prove now there is some C0 subanalytic arc satisfying that. So this is a hardest part. So I will prove that. Okay. Any question about that? No. Okay. So to prove that, I use the curve selection lemma. I don't know if you know that result. I will enunciate this. Okay, let me enunciate enunciate this this result. Is a structural result on real algebraic geometry. Curve selection lemma. Let x in, you call y just to agree with my notation, y in some Rm be a subanalytic set and x just the same way, x in a non-isolate point, x in y minus p, sorry, p here is p is a non-isolate point. Okay, so if I have that, then there exists C0 analytic. In fact, I can put analytic, an analytic arc, gamma from epsilon to Rm, such that gamma of 0 epsilon is in X, and gamma 0 is P. Yeah, right, thank you. Okay. We can find a proof of this in the paper of Milman-Briston, the famous paper of semi-analytic and subanalytic sets. Okay, so I use that. I think I have to stop now, right? It's up to 25. Yeah. So we will do a break, and then we come back by proving this result, and then we will prove another one. Okay, thank you. Any question? No? Okay. So see you at Sorry, I forgot to come back. Oh? Já, acho que já está gravando. Sim, ok, obrigado. Thank you. Now I prove this proposition. Let me. I use this this map. Let me continue this. Let me continue the. After a translation, for example, I will assume, for example, P is the origin. Okay, it's. Let me assume. I'm going to prove that direction. I'm assuming now P is equal to 0. And then let me call Y the following set without the closure. Okay. So we are going to consider two cases of V. In the first case, V is different to 0. And of course, it's enough to prove if V is equal is different to 0. If I know how to prove the statement when V has norm equals to 1, it's easy to obtain the answer to NV, because we can just, if gamma, we can define gamma tilde of T like gamma of norm or V T, for example. And of course, this. Oh, we have one more blackboard. Okay, so because this, it's enough to prove when V has norm equals to 1. Okay, so and then we have the other case when V is equal to 0. But so I will prove this case. And in this case, let me remark, for example, W equals to V0 is in the set Y minus W in the closure. In fact, just to use the curve selection lemma, because if X is subanalytic, X minus 0 is subanalytic, since rho is an polynomial map, of course, the preimage of a subanalytic set is a subanalytic set. So Y is a subanalytic set. Okay, so if Y is a subanalytic set, I can apply the curve selection lemma to Y. And this is more or less easy because Y, W is not in Y, because the coordinate is 0, and there is no point in Y with coordinate 0. This the last coordinate 0. So this is, in fact, is the same of Y, the closure. So you have to, if W is in the closure of Y, we can apply. Okay. So we are going to assume in fact, we have we assumed, for example, V, right? V is in the tangent cone of X, and this means there exists some Xj in X minus 0, and Tj in Tj here, 0 plus infinity, and such that xj over Tj goes to V. And of course, by taking a subsequence, if necessary, we can assume, for example, xj over xj goes to V, because goes to, okay, it's easy because this is unbounded set. If this, you can divide now. In fact, we can. In fact, we don't need to take a subsequence. We divide by Tj and Tj here. It just goes to V. But if you consider, for example, rho minus 1 of xj, this is exactly xj over xj. Now it's easy to see that the row of a set is just rho minus 1 over rho of xj is just exactly that. And since xj is in x, this is in y. And of course, this converges to 0, and this converges to V. So W is in the closure of Y. So there is a, I use this part. Sorry for that. So by curve selection lemma, there exists some gamma from epsilon to Y closure. In fact, no Y closure to some, in fact, to Rn plus 1, such that gamma is gamma 0 epsilon is in Y, and gamma 0 is W. So let me write gamma something like that. Gamma is xt, st. No, in the coordinate. In fact, we can, for example, since x is, since Sx, gamma is analytic, and the right side of gamma is in Sn minus 1 plus Rn. Of course, gamma arrives here in Sn times Sn minus 1 times R. Okay, so this coordinate is always in Sn minus 1, because this is axiomat, right? Then since now gamma, when you take nt, in positive t, st is in y. This point is in y, so this guy is positive. St is positive if t is here, for example. And then, and of course, S0 is 0. So this is an analytic arc. This is analytic, okay? So S is analytic arc and non-constant analytic arc. So if it is non-constant analytic arc, the derivative is not equal to 0. It's not the zero map. So if S is not the zero map, the S prime, the derivative is not the, we can, for example, assume the ST is different to 0 for NT here, maybe shrinking epsilon. Maybe shrinking epsilon. We can assume that. And from this, we have that S is a homeomorphism, for example. No? The derivative is positive. So we can we have, in fact, S is from 0 to epsilon this way, from to 0 to some delta is a homeomorphism. Is homeomorphism, right? And because this is a homeomorphism and analytic, its inverse is subanalytic, for example. Okay, so I can now define the gamma in the following way. I will define gamma from 0 delta to x closure by doing the following. Gamma of t is rho of gamma of s minus 1 of t. Okay? This, no, yeah, sorry, this, sorry, so bitter. Yeah, I should call gamma beta, but no, beta. Okay. I compose it. Let me now write what means that there, right? I will write in a slow way. So let me write once again. Beta t is rho of gamma of s minus 1 t. And this means rho of x of s minus 1 t. T, right? Because we are composing with s. And now this is t times x of s minus 1t. So we have to show that when you divide by t, this goes to v. So if you show, for example, this limit when t goes to 0, this is v, we have finished the proof. Because this means, of course, the beta 0 is 0, and we have derivative, and the derivative is v. This is just to say that the gamma has derivative, and the derivative is v. But this is easy because if you, this is limit of x s minus 1t when t goes to 0, but s is continuous, s minus 1 is continuous, so this goes to s0, which is 0, and this goes to x0, but x0 is w, is v, so this is just v. Okay, so we have finished this part. But for this, for the case when v is not v0, case 2, when v is equal to 0, we still have this sequence, but now converging to 0. And then I can assume, for example, xj over xj goes to some u up to take a subsequence if necessary. Okay, that means I'm assuming that xj over tj goes to 0. So, and xj is not 0. So now I'm taking this sequence. But now U is a tangent vector with norm equals to 1. So we can apply the I case for U. And then there is beta. This implies there is beta, such that beta t is tu plus ot. And then we can define gamma as beta of t squared. If you define now, if you define gamma now has beta of t squared, of course this will be t times 0 plus ot. And tu, thank you. Tu. And then we have finished. Okay, any question? Okay. So, now I want to prove the main result of this lecture. The result is tangent cone is invariant by Lipschitz maps, by Lipschitz. Let me write the theorem here. Let X in Rn and Y in Rm be subanalytic sets. If there is a lipomorphism phi of x0 to, I will assume you are working at the origin because we can translate to the origin. So then there is a global lipomorphism I will call d phi from the tangent cone of x to the tangent cone of y. Okay. So to do that, I will need some, I cannot even pronunciate and write the names. Let me try to read the names. I will use the McShane-Whitney-Kuss-Brown theorem, which say McShane-Whitney Kuss. which say that if you have a Lipschitz map defining some set of Rn, you can extend this Lipschitz map to define it now on all Rn. Let X in Rn be a set, and H from X to Rm be a Lipschitz map. Then there is H from Rn to Rm. Sorry. Such that Lipschitz, there is a Lipschitz map such that 8 restrict to X is 8. And let me hint how to prove that. In fact, since 8 is Lipschitz, it's easy to extend to the closure of X in a Lipschitz way because it's uniform, right? Uniform and continuous. So we can assume X is closed. And also, it's enough to show the result when M is equal to 1, because we can prove for any coordinate of 8. And then we define capital 8 as the extensions of each coordinate, right? So we can assume also, and then is equal to 1. And for this, we define now 8 from Rn to R by the following. We define if, let me assume, for example, we have that, right? For nx and y in x, for this constant. I use these constants. 8x is the infimum of 8y plus c times x minus y when y is in x. So is a exercise to prove that x satisfies this Lipschitz and is an extension of 8. Capital 8 is an extension of 8. Okay? But if you want, you can read the proof in the notes. And then I use that, and of course I use also this proposition to prove our theorem. Let me hint how to prove that. I will try to. I don't want to erase this. Okay, so for example, let me denote just to use a proof of our theorem. Let me denote using the McShane-Whitney-Hurst-Brown theorem. Let me denote, for example, phi tilde from Rn to Rm the Lipschitz extension of phi. And of course, we define psi tilde now to Rm to Rn. The Lipschitz extension of phi, and the same of phi minus 1, given by this theorem. Okay? So, what I will prove is I want, for example, it's important for me to have a by Lipschitz map defined in the ambient space. So I will change a little bit x and y, and of course phi, to obtain another map which is defined now in the ambient space. And the map will be the following. I will define to Rn plus m in the following way. I think it's good to put the decomposition here. Why? Yeah, here. This will be x minus psi tilde y plus phi tilde of x, and y plus phi tilde of x. And I will define also in the same way pc of z w to be z minus z plus pc tilde of w, and w minus pc tilde z plus pc tilde w, and in fact, since, for example, this guy and this guy are Lipschitz, it's not hard to prove, for example, capital phi is Lipschitz, and also capital psi is Lipschitz. Okay? Because we have a sum of Lipschitz and composition of Lipschitz, and then this is Lipschitz. And it's easy also to prove, for example, in fact, phi composed with pc is the identity, and the converse also, the vice versa. Right? The psi composed with phi is the identity. So we found two maps now defined globally, and which are by Lipschitz. A second good property of these guys is capital phi sends x times 0 in 0 times y. If you look in quickly, if you put y 0 here and x in capital X, phi tilde is phi, so these arrive in y. If it's in y, pc tilde is pc, is the inverse, so this is x minus x is 0, and y is 0, right? And since y is 0 and x is in capital X, psi of x is in y. So of course I'm saying that x, y is in 0, y. Of course, when x is in x. Of course, we can do the same when you are in, when we put y0 for capital psi, and this and because they are inverse of the other, we obtain equality, just equality. So this is why. And then I use the property, for example, the tangent cone of the product is the product of the tangent cones. And so you prove, for example, I will obtain now a bi-Lipschitz map from x times 0 to 0 times y. And of course, that map will induce a bi-Lipschitz map, the tangent cone of that product. I will find a bi-Lipschitz map from x times 0, that's what I'm saying, to the tangent cone of y 0 times y 0. And of course, since this is tangent cone of x times 0 and tangent cone 0 times tangent cone of y, this induces a map from the tangent cone of x to the tangent cone of y. So how to obtain this guy? And for this, I will define for nk natural number, I will define phi k of Rn plus m to Rn plus m in the following way. Phi k of v is k. Let me put pck also. Phi of 1 over k v. And pc the same. Now pc k of v is k capital pc of 1 over k v. And since PC is globally by Lipschitz and PC is globally by Lipschitz, there are constants, let me call a constant C, the biggest one of PC and PC minus 1 and phi minus 1, in such that here. So, in fact, there is so constant greater than 1, such that 1 over c u minus v less than pc u minus pc of v less than c times u minus v, and the same for pc, 1 over c u minus v pc of u pc of v. Okay, and if you now look phi k and pck and now do the change, the same inequalities holds to pck and phi k with the same constant, because and here we are multiplying by k, but here we are dividing by k, so that means I could put, for example, now pck, phi k and pck for nk. But this is a family of functions with the same Lipschitz constant. So if you restrict to a compact set, we can use as a last call theorem to obtain a subsequence which is convergent. So, for example, if you are in the ball, the unit ball, the closed unit ball, there is a subsequence such that psi kj converges to some d psi and pc of kj converge uniformly to the psi. Here in the unit ball, and here let me put in the ball of radius c. C is the constant here, for example. And then we can now look this this subsequence. Let me put just K1, just to put 1 here, because I'm talking about the ball of unit ball. And now for the ball of radius 2, we can extract a subsequence of this one, which now we have in fact now uniform convergence now in the ball of radius 2, and so on, so on. What I'm saying is I can obtain now no, I erase. I put here. So in fact, I, for example, can obtain a subset of kj L, a subsequence of kj L minus 1, such that now psi kj L converges to the phi L in the ball of radius L, and of course the same for kj L converge here in J, right? In J also. In the ball of radius LC. So you can, for example, now take the diagonal subsequence of these guys, and for example, we can show, for example, phi of kj converge in compacts to some map the phi, and the same for pc. Converge in compacts now. In compacts, no uniformly in a ball, but in compacts, some pc. And then we can show for these maps satisfies the properties that we want. This map is a bi-Lipschitz homeomorphism from, in particular, right? And this is also is a map from Rn plus m to Rn plus m by Lipschitz with the same constant c, and of course we can use now a combination of this proposition to prove. For example, it's enough to prove if you take in fact we can prove, for example, the inverse of this guy is this guy, because the limit is uniform. So you can, and of course, I did not say that before, but if you compose phi k with psi k, this is the identity. So if you put a limit here, you show, for example, the psi is the inverse of the phi, for example, right? And just to finish, I think I My time is almost in the 3 minutes. I just, as I said, this is just the inverse of the psi, the phi. So it's enough, for example, to show that the image of the tangent cone is contained in the tangent cone of because then we apply the psi and we obtain the equality. And if you now take a sequence here, you take a vector v0, for example, here, we can obtain a sequence. In fact, no a sequence. We can obtain a continuous. If you take now a vector here, I want to prove that the v of v is in this set. So we obtain this guy such that gamma t is v0 t plus ot. Simple. And this it's not good to write this because it's I only show that. And then TV. Okay. So if you now consider the phi, you will now consider the phi of gamma t minus pc of TV. Let me call Tj 1 over kjj. Just that sequence of this guy. So if you put now Tj here and use the Lipschitz TV, the Lipschitz condition. For example, this guy, when you divide by Tj, this is just phi kjj of v, for example, when you divide by Tj. So if you use the equality, this is constant times the difference, but the difference is something like T O Tj. So this is O Tj. That means if you divide by Tj, this goes to 0. So if you divide by Tj and you divide by Tj, this goes to 0. So this limit is equal to this limit if there exists. But this there exists because this goes just to the phi of v. The phi of v. Right? Because this is Tj when you put is 1 over kjj times kjj. And the limit is just goes to the phi. But now this guy, when gamma is applied in Tj, this is now in x. And when apply phi, this is in y. So this guy, if this limit exists, the limit is in the tangent cone of y. But it's the same. So this is showing that this is the tangent cone of y. And then we have finished the proof. Thank you very much. I have to run this in the finish, but in the end of this, and I'm fat. Any question? No? This is bad. Because in general, in my experience, if there's no question, it's because you understand everything or you understand. Yeah, because, yeah, the point is, I took the diagonal sequence of, you obtain, for example, a family of subsequence of natural numbers. And then we took just the diagonal subsequence of numbers. And for that sequence, let me call, for example, this is maybe Sj, for example, is a sequence of natural numbers. For that Sj, we prove it, for example, we prove it that for that Sj, phi of Sj converges in compact to the phi in compacts. So now I'm taking Tj to be 1 over Sj, Kjj. This is Tj. And if you now look at J, just as now, this is just to maybe the confusion is here. No? If you multiply Tj times V over Tj, this is Kjj phi over Kjj times V. And this is phi over Kj J over V of V. This is what I use it here, right? Because this converges to this guy. Okay? Any other question? No? No microphone?
So all the results you made here are not, apparently they are not specific for the real field. I mean, apparently you need an ordering, but all this geometry could this geometry be generalized for any real ordered field?
The point is, we have used it as a last call theorem. And if you are in a general field, I don't know if you have that theorem.
Yeah, but if you are in a real ordered field?
Yeah, even if you are in that, I don't know if you have. I think
about the field of convergent series.
Yeah, maybe.
Real coefficients.
Yeah, maybe we don't have. We don't have. I don't know, but I think in general, even in an ordinate real field, we don't have as a last call theorem.
Okay.
Do you know, Alexander, something? No. But my feeling is, yeah, Tim.
We have also a question. So if we are at a smooth point and the tangent cone is just a tangent space,
Yeah.
then we could approximate the Lipschitz function by a smooth function, and then the induced map on tangent space is just a differential. Is this somewhere like obvious in this proof?
Yeah,
By this kind of technique that you used?
If you are in smooth points, that's easy because the tangent space is always a k-dimensional linear space. So, of course, we have two k-dimensional linear space are diffeomorphic.
But the thing you constructed in the proof, is it kind of like obvious that what you constructed is a generalization of this differential?
No, in fact, this is more or less the obvious generalization when we are in the case that here. Yeah, I think it is when the map is subanalytic as well. It's by Lipschitz and subanalytic, and in this case, of course, we have some kind of well-defined Lipschitz derivative. When phi is Lipschitz and subanalytic, we can define something like exactly this was defined by Bernig and Litschak. The Lipschitz derivative we can define if you take v in the tangent cone, and you take now any arc to x satisfying that tv plus ot. When you compose phi with gamma t, if you are assuming that phi is Lipschitz and subanalytic, locally this is subanalytic as well. And then since we have this is a bounded arc, this is a bounded arc, you can prove, for example, this is a bounded subanalytic function. If you have a bounded subanalytic function, we always have a limit. So you can define the phi of v has the limit of this guy. And this definition does not depend of phi when, does not depend of gamma when phi is Lipschitz, because if you take another one and then you use the condition, it's easy to prove that does not depend. So this was the idea was not define of this derivative, but now without assuming the phi is not subanalytic. So if phi is not subanalytic, we don't have this definition. So everything was done to try to recover something like that. And in the end, we obtained something like that. But for specific gammas, this was, for example, if you are in the curve arcs with velocity v, which is the gamma t equal to tv. And since we are now in the case that you don't have a subanalytic property, we cannot obtain this kind of limit. So I try to prove something like that for one specific case, what was this guy. And this is not for all the curve, but at least for the curve in a discrete way. This was
Thanks.
welcome.
One thing about what Edson explained now. For instance, when you are in the subanalytic case, the derivative is unique. You have only one derivative. But when you're not supposed the map is subanalytic, you can have more than one derivative. It's not unique. For some different sequence, you do a blow up like that, you arrive in another derivative.
Yeah, and before we don't know even if there was a derivative, but now we know there is, and but it can be not unique.
So it's more or less the same comment as Alex. So the subanalytic case, the construction is functorial in some sense, no? It's
Yeah.
numerical.
Yeah, yeah.
But in the general case, it's not, no?
No, yeah. Yes. In fact, one more comment. In fact, we can, for example, present two sets that are by Lipschitz homeomorphic, but are not subanalytic by Lipschitz homeomorphic. We can present this kind of sets. And this shows, for example, this theorem is not an adaptation, in fact, of the theorem of Bernig and Lichtschak, because there are sets which are by Lipschitz, but are not subanalytic by Lipschitz homeomorphic. Okay. Okay, Ashki. No question? Okay, thank you.